Hello and welcome everyone to the CS Research Day presentation. My name is Rohit and I will be demoing and presenting a work done by me and Professor Lin Trong on Security-Elasticity Dependencies Analytics for Industrial IoT Systems. Alright, so what is the motivation of our work? Well, basically, we all know that an industrial IoT network has multiple sensor layers. They might have a heterogeneous edge layers and very wide artifacts for cloud layer. What currently we need is an end-to-end observability of dependency among the components. Now these dependencies can be intra-layer, such as between the database and the broker on cloud, or it could be interlayer, such as the dependency between edge artifact and a cloud artifact. Currently the research is mostly focused on individual subsystems or layers, so they generally don't talk about interlayer dependencies occurring between the components of the IIoT network. This slide here presents a brief snapshot of what an industrial IoT infrastructure might look like. So we have a sensor layer here that publishes some data to the edge layer, and edge layer has its own microservices that perform some local processing and further sends that data to the cloud. The cloud has its heterogeneous pipelines and other complex infrastructure that does streaming, ingestion, batch processing, and presents the data to the clients in a dashboard format. What we are trying to do here is to analyze a cross-system dependency of security and elasticity. So for example, what happens if there is a compromise of the IoT data hub? How will that Cassandra storage be affected from that issue? Or if there is a issue on the edge analytics, how will that reflect in the Apache Spark batch processing here? So basically we are trying to establish cross-layered, cross-system dependency of security and elasticity across the whole industrial IoT infrastructure. Okay, so to perform the security elasticity analytics, we needed to first model these dependencies using systematic methodology. So for that, we chose W3H techniques, which refer to what, where, when, and how of an incident. So for example, due to unsecured broker, the what characterization can be incorrect stream analytics or a decreased broker throughput. The where characterization refers to where the incident will take place. So the incident might take place at the IoT or edge broker. The when characterization, well, it refers to the frequency of the issues. So at the runtime, there can be performance changes due to unsecured broker or unnecessary scaling operation due to some rogue entity performing attack on the unsecured broker. How is the last characterization that we do, and that includes how we can see these incidents. Well, for that we need an end-to-end observability across the three layers, and that includes the message broker, data ingestion pipelines, etc. So next we will be looking at the Aalto SEA framework. So the Aalto SEA framework has many different components, and to keep things brief, we have the DevOps task that has to be done by the developers to utilize our framework. We have models and configurations that are provided as a part of our framework, and we have plugged components that are provided as framework, but the developer might then choose to use his own plugged component. Next thing that we look at is the experimentation for an unsecured broker, and how we analyzed the data using our framework to arrive at certain dependency. Okay, so here we have a sample dashboard of the elasticity of our industrial IoT infrastructure under normal condition. So we had certain edge brokers at different locations. We had Kafka and Cassandra database at our cloud, and then we varied the elasticity of the system by increasing the number of sensors. And we can notice how linearly the elasticity of the cloud increases, and then it also decreases. So here is the graph that we obtained during the attack scenario. We varied the number of healthy sensors in the same fashion as we did before, but here we introduced some poison sensor that we're publishing onto the Frankfurt Edge broker and changed in the same fashion as it did before. It increased linearly and then decreased in the same manner with the decrease in number of healthy sensors. So basically, looking at this graph, the developer would then conclude, yeah, the effect of unsecured broker is not really visible on the cloud layer. We performed the analytics and then we came up at this plot here. So if we look closely at this plot, while the elasticity of cloud might seem the same in both the conditions, but we can notice that the under the attack condition, the graph is a bit slower to respond to the scale down operation. That might be due to higher throughput through the edge broker translates to slower publishing rate on the cloud, so it took some time for the messages to get clear. Another very subtle but very important thing that we noticed was the sharper peaks that happened on normal conditions were replaced by plateau of peaks. So the important thing here is the rate of ingestion remains same, and the developer would not notice that, but the rate at which the data was being published changed this time because of longer processing times that are still less than the batching time of the cloud artifacts. So that was it for our presentation. So if you have any suggestion or any doubts, please feel free to contact us on these locations. Thank you.